So can I share my screen?
Please.
Yes. All right, I share my screen. So I will write on my tablet for the talk. So thank you for the invitation.
Yeah, sorry, Eddie. Could I please ask everyone just to mute and so that, yeah.
Is it okay? Okay, yes, all right.
Yes, good. I've muted myself.
All right. All right, so I want to talk about a recent work on loop soup on a metric graph. And I will be actually interested in Markov property of a loop soup at a critical intensity, which is 1/2, and for which the loop soup is related to the Gaussian free field. So first I will introduce a model. So I will be just in a discrete setting where I take some graph G, a finite graph. All right, so for example, a box in the planar lattice. Okay, so I have a graph. Okay, let's say I take a box. And finite number of vertices and finite number of edges. And instead of looking just as the graph as a set of vertices with edges, I want to look at it as a metric graph. So I want to look at it as a metric graph. So maybe I can draw a picture on another page. So that's my graph. And actually, I will look at it as a metric graph. So what does it mean? It means that actually, instead of just looking at vertices, at nodes in my graph, I will consider also any point in the which lie on the edges. So let's say I call it S. That's a set of points which are either a node, so a vertex, or a point on an edge of the graph. So I will consider that my edges have some length. So an edge E has some length. I call it rho E, for example, have some length. And I look at all the set of points which lie on the edge or which is a vertex. And that's a metric graph. So I have a graph with a distance, a set of points, a set with a distance. It's a metric space. Okay, and so now what I'm going to do is I'm going to look at the Bronian motion on this metric graph. So I will look at a Bronian motion which travel along the edges of this graph. And for example, so I want to kill my Brownian motion somewhere, so I can just add, let's say, a point, V0, and I say that I suppose that my Brownian motion is killed when it hits V0. Okay, so I'm looking at the Brownian motion killed at V0. So locally, it's just a Brownian motion on the edge. So it's like a one-dimensional Brownian motion.
Sorry, Elie, are you using two devices?
Sorry?
Are you using two devices at once?
All right, so I have a Brownian motion on the graph. So locally, it's just a Brownian motion on an interval, let's say. And then at a node, it makes excursions. It makes excursions along the edges, and then it will then there will be one excursion which will cross an edge and so on. So you can define a Brownian motion on T-space. All right, and you kill it when you hit the distinguished vertex V0, let's say. All right, so I hope it's clear so far. And so if I have a Brownian motion, I can define the probability transition densities. So that's the probability starting from a point X that my Brownian motion at time t, is at y. And you suppose that at time t, you didn't hit V0.
We have a question here, Elie, sorry. Are you happy to take questions now? Would you rather have the...
Yes, please. It's better, yes.
Okay, Kostya, go ahead. Go ahead, Kostya.
Thank you. Elie, how does the Brownian motion decide along which edge to continue when it hits a vertex?
Yes, so you take it uniformly. So a way to construct it is just with excursion theory. So you are at the vertex, and then you just have excursions. So it's one-dimensional excursions, and so you can construct it just from one-dimensional excursions, and then each excursion you choose uniformly a vertex for the corresponding excursion. So it just chooses, it's a Brownian motion, and it chooses edges, adjacent edges uniformly. Yes. Okay, so you have some probability transition densities, and then you can define a loop measure. So this loop measure will help us to define the loop soup. So you can define a loop measure. So it will be a measure which is defined as, first, you take a point in S. So S, I recall that that's a set of points which are on the edges or vertices. Actually, since it will be an integral with respect to the Lebesgue measure, you can consider X as being a point on the edge, on an edge. So you take a point X with respect to the Lebesgue measure, and then you take a time T. You divide by T. So T is positive, and then you take the probability transition density from X to X at time T. And then you take a bridge of duration T starting at X and ending at X. So a bridge from X to X of duration T. Is it okay? So it's a measure on bridges from a point of the graph to itself. So instead of calling it a bridge, we call it a loop. So that's just the definition. So you take a point X with Lebesgue measure on the graph, and then you decide of the duration of your bridge using T's density. So here you decide the point X, then you decide on the duration of the bridge, and then once you have the point, the starting point and the duration, then you take a bridge from x to x of duration t and condition on not hitting v0.
Can you explain to us the one on t? What
Yeah. Well, can I explain it? It is 1 over t. I think intuitively it is because you want to have loop, unrooted loop. So here, when I define it, I root my loop at a point x. So you have a starting point, which is x. But actually, you want to look at loops which are unrooted. It doesn't, for you, it doesn't matter where the starting point is. So the 1 over t is a way to say that actually I take a time uniformly because the loop has duration t, so you take a time uniformly between 0 and t. So it's a way it's a way to reroute the loop at some point. Instead of saying that I root it at x, when you have 1 over t, it will be, you will be able to route the loop at another point. So I can give an example actually of a loop measure, which is on the real line. And we will see that actually if you reroute the loop at another point, it will have a nice expression. But this 1 over t is important. It has to be here indeed. And so what I want to say also is that the loop measure is infinite because of the small loops. It's like the excursion measure for the Bronian motion. It's infinite because of the small excursions. So here it's infinite because of the small loops. All right, so maybe I can give now an example when of the loop on the real line, of the loop measure on the real line. So I keep the expression of the loop measure. And so let's look at the real line. So let's look at the positive half line. So I don't have a finite graph here. I have an infinite graph, but you can also define the loop measure. And when you kill your Brownian motion at 0. So here you just have a Brownian motion. You just have a Brownian motion on the line. All right. And so you can define as well the loop measure associated to the Brownian motion on the line killed when hitting 0. And so actually it has a nice description, this loop measure. So I look at the loop measure on the positive half line. And what you can do, so what we had so far was a point x. So we were, let's say, in the general setting of a graph. I had a point x, and then I had a loop from x to x. So I had the point x, and I had a loop. So you can say that your loop is rooted at x because you first choose x, and then you choose your loop, or your bridge from x to x. So that's the same on the positive half line. You choose some x, and then you choose a loop from x to x. But what you can do, instead of having a loop rooted at x, you can reroute your loop at its minimum. All right. So you have a loop rooted at x, and now what I'm doing is I don't care about the starting point and the ending point of a loop. So I root my loop at the minimum. And I want to understand what is the loop measure when I root my loop at the minimum of the loop. Is it okay? Okay, so I'm going to describe the loop measure when I do that. So description of the loop measure. Actually, you will choose the minimum of my loop with Lebesgue measure. Well, with Lebesgue measure. And then once you have the minimum, the loop, so the loop, because you are at the minimum, the loop will be an excursion above the minimum. And then choose excursion above the minimum with just the Ito measure. So the Ito measure, but restricted to positive excursions. So you see that it has a nice expression when you reroute the loop at the minimum. It has a nice expression. You just take the minimum with respect to the Lebesgue measure on R plus, and then you choose an excursion above the minimum with the Ito measure of the standard Brownian motion. Okay, so you choose the minimum and then you just draw an excursion, a Brownian excursion above. And that's your loop measure on R plus. All right. Okay, so that's for the loop measure. So the loop measure is just a measure on the space of loops. And when you have this loop measure, you can define a Poisson point process of loops with intensity, this loop measure. And that's what we call the loop soup. So the loop soup, it's a Poisson point process with intensity. So there is a parameter C, just a parameter, which is the intensity. And so you take a Poisson point process with intensity mu C times the loop measure. So you will have a collection of loops. All right, so you have a graph, you have your graph, and then you have a collection of loops on your graph, a collection of Bronian loops. So there will be an infinite number of small loops because the intensity of small loops is infinite. And yeah. I hope it's fine. So maybe I can look again at the example of.
Sorry, and these are unrooted loops, right? They're all.
Yes, so you do as you wish. You do. So you can see it as rooted if you want, or unrooted. Then yeah, but it's better
just trying to think how we could link the Poisson to the graph, the original graph. If they're unrooted, you can't attach them to these loops.
So I have a graph. So how I introduced the loop measure first was I was taking a point X, and then I had a loop on X.
Yeah.
So here you have a distinguished point on your loop,
yeah.
But you can just erase it. You can just forget about it. And so you look at the projection on just loops without thinking about the starting point. Yeah, but actually it's a better way to see it indeed. Look at loops without any starting point. So let's look at again the example of the positive half line. So now I have a Poisson point process with intensity C times the loop measure. So what we said is the loop measure on R plus is just I take minimum with Lebesgue measure, and then I add an excursion above the minimum. So the intensity here, the intensity C, will tell you that now you take, so how you can see your loop soup on R plus, you can take a Poisson point process with intensity C dx, so that's for the minimum. And your excursion above the minimum will be given by the Ito measure. So that's the excursion above the minimum. So in some sense, what you are doing, you are throwing at rate C. You are throwing at rate C excursions, Bronian excursions. Sorry. 是的，什么？也是的，快乐，大快乐，谢谢。你可以关门吗？你可以关门吗？你可以关门。Sorry, I have a problem with my door.
Speak Chinese too.
I think it didn't understand my Chinese, but I tried. So at rate C, I have some Bronian excursions. So yes, so it's a Poisson point process with intensity C dx, cross product with Cartesian product, tensor product with the Ito measure. Sorry.
门禁卡。
是的。Well, and so actually there is a connection. There is a connection with branching process with immigration. So you can think of it, a Bronian excursion. You can think of a Bronian excursion as a critical branching process. So a Bronian excursion is related to a Bronian tree. So a Bronian excursion, you can think of it as representing a branching process. And then when you are throwing this Bronian excursion along the positive half line, what you are doing actually is you are looking at a branching process with immigration. Well, so it's just a connection with, so you have a connection between loop soup and branching process with immigration. Each Bronian excursion, you can think of it as a family of branching process. All right. Okay. And maybe I can develop a little the example of the positive half line. Sorry, just 1 minute. I can develop a little this example because actually what you can do, so you have this Poisson point process of Brownian excursions. And what you can do, actually it's in a paper of Titus Lupu. What you can do is you can order this Brownian excursion with respect to their minimum. So here I will have time and the vertical axis is a space. And so I will have Brownian excursions and I order them with respect to their minimum. So I hope you understand what I'm doing. I have this Poisson point process of Brownian excursions. And I order my Brownian excursion with respect to their minimum. And I concatenate the Brownian excursions. Is it okay? So you add the loop soup the loop soup on R plus, it was just a collection of excursions. These excursions, so you can see loops as excursions above their minimum. And what I'm doing now is I'm concatenating these excursions with respect to their minimum in increasing order of their minimum. Do you see what I'm doing? All right, so you have a collection of loops, and then now what I'm doing is I'm following the excursions in the order of their minimum, and I get a process. I get a process. Yes, I get a process, and actually this process was studied in the 90s. It's called the perturbed reflected Bronian motion. So instead of looking at a loop soup on the half line, what you can do is you can study this process in time, and you can. So when you have this process, you can recover the Brownian loops by saying that you look at the excursion above the infimum process. So that's a future infimum process. So when you look at the excursion of your process above the future infimum process, that's the loops of a loop soup. So it's actually a way to construct the loop soup as well. You can construct first this process and you say that the loops are the excursion above the future infimum process. So is it clear? So the link between the loop soup and this process, I'm just concatenating the loops in increasing order of the minimum. Okay,
sorry,
and what?
I'm not sure I understand the future infimum process here.
Okay, so when you have a process, all right. Let's say I start with my process. So actually, it is perturbed reflected Brownian motion. You can construct it in terms of a reflected Brownian motion, and you add the local time, but I don't want to say it. So it's just a process. And this process will go to infinity, actually. It will go to infinity. And now the future infimum is just the infimum of if my process is x, the future infimum is just the infimum of my process.
Yeah, okay.
Yes.
Yeah.
And so that's something like this. And so when you look at the excursion of your process above the future infimum process, you get loops, you get excursions. And so when your process x is what we call the perturbed reflected Brownian motion, the excursion above the future infimum process form a loop soup. Okay, that's just what I wanted to say. And but now what I want to say, a last word about the case of the real line is that you have some Markov property. What is this Markov property? So you have a Markov property in space, actually. Okay, so let's do another picture. I want to talk about Markov property for loop soup. So suppose that I fix a point x in space. And I'm looking now at the loops above X. And I want to know the law of my loops above X conditionally on what happens below X. All right. So instead of looking at the loops, I can look at my process X, and I'm looking at the picture of my process X above X, above small x. So I want to look at the law of the process X above small x conditionally on my process below X. And here there is a kind of Markov property, meaning that actually to have the law of your process above small x, you only need to know the local time of your process at level, well, let's say I call it y, but it's less confusing. To know the process x, the picture above y, you only have to know the local time of your process x at level y. So when I talk about the process x above y, actually I close the time gap. I don't care about the time. I'm just interested in the excursions above y. So how can you reconstruct the process x above the level y? What you just have to do is you just take Bronian excursions up to the local time given by the local time of x, the total local time of x at level y, and then you add you add the loops that with minimum greater than y. So you can reconstruct the picture above level y just knowing the local time at y, and it will be independent of what's below level y. So that's what I call a Markov property. If you want to reconstruct the picture above level y, then you just need to know the local time at level y, and then it will be independent of what happens below y. So it's a Markov property. So to reconstruct, the excursion above y are just Bronian excursions, and then you have to add the last part, which is actually measurable with respect to the loops with minimum above y. So it's a Markov property, and actually this Markov property holds, in the case of the real line, it holds for any intensity. So if you take a Brownian loop soup with intensity c for any c, then you have this Markov property that if you cut your process at some level y, then conditionally on the local time at this level y, what happens above and below are independent. So maybe I can make a picture with loops instead of this process x. What did I do here? I look at my loop soup on the real line, on the positive half line, and I'm looking at a point y, and then I'm focusing on the loops which intersect the space above y. So there will be some loops Okay, so for example, I have a loop like this with minimum below y and maximum above y. And what I do is I cut this loop. When I cut this loop, I will have excursion above y. Okay, so now I just look at the picture. Maybe here I have another excursion. I just look at the picture above y. So loops will be cut into excursions. And then there will be also loops with minimum above y. And so I'm just interested in the picture above y, meaning I'm looking at the excursions above level y and at loops with minimum above y, minimum greater than y. And I'm saying that the law of this picture, the law of the excursions and the loops with minimum greater than y, conditionally on the local time at y, is independent of what happens below level y. So it only depends on the local time at y. So that's what I call a Markov property in space. So it's a kind of a consequence is that you have a very nice theorem, meaning that if you just look at the local time of the loop soup at each point, it will give you a Markov process. All right, so if there's something to remember is that you have a Markov property for the loop soup on the real line at any intensity. If you know the local time at a given point, then the picture of your loops above y is independent, conditionally on this local time, is independent of the loops below y. And that's what I call a Markov property. And so now I want to know, is it possible to have a similar Markov property, but in the general case of a graph? So I want to know whether I have a Markov property for a general metric graph. So that's the question. Okay, so I will state my question. Is it possible to have a Markov property for the loop soup on a metric graph? Okay, so the answer is no in general, but there is a special case which is a case when the intensity is equal to 1/2. And actually this special case is related to the Gaussian free field. And so for this intensity, then you will have indeed a Markov property. So that's what I want to present now. So first, what do I mean by Markov property for the loop soup on a metric graph? So suppose that you have a graph. And suppose that you look at a subset of the graph. And you want to look at the loops outside this subset. So here I have a subset of the graph, and I look at the trace of my loops outside this subset. So I will have some excursions like this, or also I have some loops which do not intersect my subset. All right. So I have a metric graph. I take some subset, a fixed subset of my metric graph, and I look at the trace of the loops outside my subset. All right. What are the trace of the trace of the loops? Consists of loops which do not cross my subset. So it is easy because you have a Poisson point process, then it's just a Poisson point process in the complement of my subset. So these loops are not interesting for us actually. What is interesting is the trace of these excursions outside my subset. and I want to know, is it possible that these excursions, the law of this excursion only depends on the boundary, the local time, let's say, on the boundary of my subset. And so that it will be independent of what's happening inside the subset. So I hope you understand the question. For the real line, that was the case. So I was looking at the interval 0, y, and I was saying, if I know the local time at y, the picture outside the interval 0, y is independent of what's happening inside the interval 0, y. So now I'm asking the same question for the graph. I have a subset of the graph. I look at the excursions outside the subset. Is it possible that the law of the trace of the excursions of my loops outside the subset only depends on the local time, on the boundary of my subset, and not on what's happening inside the subset? Okay, so that's the question. So first, actually, the answer is no. You cannot have something so strong. So I will just do it on a simple example, which is the example of a circle. So I will rephrase my question just for a circle. I have a circle. I have a Bronian loop soup on my circle. And let's say that I fix the local time at a point of the circle to be equal to L. So L is fixed. And what I want to do, I fix some arc. Okay, I fix some arc, and I want to understand the law of the loops, the trace of the loops outside this arc. And I want to know, is it possible that the distribution of this excursion only depends on the local time on the boundary, meaning on the local time at this point and at this point? Then actually it's not possible. And is it, and is it independent of what happens inside the arc? So you cannot have something so strong. So why? Actually, there will be problems of parity. Yes. So let's say, for example, that at some point you have local time 0, meaning that at some point, suppose that at some point there is a point, for example, this point which does not belong to any loop. So suppose that you have local time 0 at some point, and therefore you know that this point was not crossed by any loop. Then it will give you some information. It will give you the information that you didn't have a cycle, you didn't have a loop who did that. Because if you have a cycle in the circle, then you know that every point of the circle will be visited by a loop. So if you have a point with local time 0, meaning that if you have a point which does not belong to any loop, you are sure that there were no loop made visited the whole circle. So if you have 0, it gives you an information on what's happening outside. It gives you the information that actually, if you look at the number of crossings from this point to the other point, it will be necessarily even. So you will have an even number of crossings. If you have 0 local time, you know that if you have a loop, this loop cannot cross this point here, and therefore, when you have a crossing from this point here to the other point, then you have to come back. And therefore, the number of crossings will be even. So it gives you an information. What's happening inside the arc gives you an information on the parity of the number of crossings from one point to the other. So I hope you agree that it means that you cannot you cannot have a Markov property in the strong sense I was hoping for, meaning that what's happening outside the explored arc only depends on the local time at the boundary. That's not possible, because if you have a 0 in the explored arc, it will give you information of what's happening outside. But actually, what I show in my paper is that that's the only constraint that's the only limit for the Markov property. So if you suppose that actually in the explored arc, you don't have any 0 for the local time, then there will be a Markov property. So that will be my result. So let's try to just state it in the case of the circle. So I have some arc, and I suppose that on this arc, I suppose that the local time is positive. So you have an arc, and you suppose that, so you have your Brownian loop soup on the circle, and you suppose that the local time is positive on the arc. Then, actually, it's true that you have a Markov property. And that's only valid for the critical intensity, which is 1/2 actually. So what is this Markov property? It states that if you look at the trace of the loops outside the explored arc, so you can also have crossings like this, then the law of the green curves only depend on the local time at the boundary of the arc. And it will be independent of the occupation field of the local times inside the arc. So that's the Markov property I want to state. You have, in the case of the circle, you look at an arc, and you suppose that the local time is positive on this arc. If it's not positive, then you can't have a Markov property. But you suppose that the local time is positive on the arc, then the trace of the loop soup outside the arc, conditionally on the local time at the boundary, is independent of the occupation field inside the arc. But I don't say that it's independent of the trajectory of the loops inside the arc. That's not true, but it's independent of the occupation field. And so in the general case of a general metric graph, so you have your metric graph, and you take a subset, and you suppose that the local time in the subset, so let's say that this subset, I call it B, the local time in B is always positive. Then you have a Markov property. And that's also just for intensity 1/2. Meaning that if you look at the trace of the loops outside B, the distribution only depends on the local time at the boundary of my set B, and it will be independent of the occupation field inside B. It will only depend on the occupation field on the local times at the boundary of B. So that's a Markov property. Actually, you can, it has a nice, the distribution of this excursion is really simple. When you suppose that B is connected, it's just the number of excursions that you have. It's just Poisson distributed. So it's very, yes, it's a very explicit distribution. Yes, so that's what I think I can stop here.
Thank you, Elie. That was great. Thank you. Really interesting. Very well presented. Questions, comments?
Instead of the circle, what happens if you considered a rooted tree? My naive feeling is that what's happening on a rooted tree would exactly be what's happening on the positive real line.
Yes, so indeed, when you don't have any cycle, then this Markov property is very strong. It will be also hold for a tree at any intensity. So the problem is just cycles. The problem in the general setting is cycles. When you have cycles, then you don't have a Markov property.
Depends on the topology of your graph.
Yes. So without cycles, you have a Markov property. This Markov property is very is valid in a very strong sense, meaning that actually the trajectories themselves are independent and at any intensity. So it looks like the real line.
But likewise, if in the real line you took a segment rather than half a line, you would have the same problem.
Yeah, so with a segment, yes, it works as well. So you can look at for example, you just look a loop soup in an interval, and then what can I do? Yeah, I explore this region, and I want to know what's happening.
Yeah.
Outside, and it will be independent of what's happening inside when you condition on the local time at the boundary. So actually, these Markov properties were proved in the case of the perturbed reflected Bronian motion that I mentioned earlier. So that was before the loop soup, and then after there was this connection between loop soup and this one-dimensional process by Titus Lupu, and it gives you for free the Markov property of the loop soup on the real line. So the problem is when you have cycled in your graphs, then the Markov property doesn't hold anymore. And actually, even at C equal 1/2, the Markov property is not a Markov property in terms of trajectories. You can just say that when you explore some subset, what's happening outside depends on the local time on the boundary and is independent of the occupation field. But it's not true that it's independent of the trajectories inside. It's just independent of the occupation field inside the explored region. There's actually the only problem is the problems of parity. If you look at the trajectory, you will have information on the number of the parity of crossings, or that's the only problem actually with graph with cycles. And that's only at intensity C equal 1/2. Otherwise, it's not true for other intensities.
And what's the significance of the half?
Yeah, so it's because you have these isomorphism theorems which relates local times of loop soup with the Gaussian free field. And the Gaussian free field has a Markov property. So Gaussian free field is just a Gaussian process with covariance given by the green function. And we know that it has a Markov property. Actually, that was the purpose of this work. I wanted to know, because I know that the Gaussian free field has a Markov property. So I know that in some sense, local times of the loop soup have a Markov property. But can we say more? Can we extend this Markov property to the trajectories themselves instead of just the local time? And actually, yes, it's true. You have a kind of Markov property for the trajectories of the loop soup. So yes, this intensity is very particular. So for example, in the real line, when you take this intensity, the local times, so you have a very nice theorem, meaning that the local times, so it's a process in space, the local time process. It's actually a Bronian motion, the square of a Bronian motion. So it's a very specific intensity.
Thank you.
Guys, may I ask a question?
Please do.
Oh.
Thank you very much, Elie. That was a really nice talk. Gave us a bit of an idea of what all these really interesting objects are and what they do. Thank you very much again. And yeah, please join me to thank Elie.
Thank you.
And we'll see you next week.